Hello guys, in this video we'll talk about your 9th lab. In this lab we will be implementing a part of VerySimpleCPU. In this implementation we're going to only have 4 instructions. These are add, addi, bzj, and bzji. Once we have completed this, we will be able to run assembly programs on your FPGAs. Before we get into designing this, we should remember the architecture of VerySimpleCPU. In this figure, we can see the structure of VerySimpleCPU. It has 2 main components, the core and the memory. The core is where the instructions are executed. This is represented by the file VerySimpleCPU.v in your lab. As for the memory contains your program and your data. This structure is represented by blram.v, which stands for block RAM. This means that you will be writing your program in this, as well as your data. And the contents of your memory are stored in the file data.v. In order for the core to communicate with the memory, we have the following communication ports. In order to select which address to write or read to, we have address to RAM signal. As you can see, this signal is a 14-bit signal. And then we have 2 data signals, one for data to RAM and the other data from RAM. Data to RAM is for writing into the memory. Data from RAM is the data you receive from your memory. As for our final port, write enable, this indicates that we want to write into our memory. In order to read a specific memory, let's say we want to read address 5, we would write 5 into address to RAM. We would disable write to enable, meaning that we would write 0 here. And then after 1 clock cycle, we would receive the contents of the address 5 from data from RAM. If we wanted to write something, let's say we want to write 15 into address 5, we would write 15 to data to RAM, and then write 5 into address to RAM, enable write enable, meaning that writing 1, and that's it. In the next clock cycle, the value 15 would be written into address 5. Next up, let's look at how our instructions are written in VerySimpleCPU. So, as you remember, our instructions are a total of 32 bits, starting from the 0th bit up to 31st bit. And in these instructions, we have our opcode, our I bit, A and B. Our opcode indicates which instruction we are using. The I bit indicates the immediate mode. And A and B are the values to work with the instruction. As you can see, the opcode is 3 bits, the I is 1 bit, and A and B are 14 bits. Next, we will review the instructions we will use for this lab. First up, we have the add instruction. In this instruction, we take 2 arguments, A and B. We look into the value of A and B, add them up, and then write them back to A. So if we were to say, right, add 10, 15, we would look into the address 10, we would look into the address 15, add them up, and then write them into 10. So if 10 was 3 and 15 was 2, once we execute this, this would turn into 5. Next up, we have the immediate version of the add instruction. In this instruction, we use the value inside A and just the value of B. So if you were to do a similar example here, add I 10, 15, again is 3, 15 for this is not important. The value of 15 is not important, so let's say it's 2. So it is not going to add 3 and 2, it is going to add 3 and 15, and then it will write it back to 10, meaning that 10 will be 18. Next, we have our BZJ instruction. BZJ stands for branch on 0. So what this does is, if the value inside B is 0, then our PC, our program counter, will be equaled to the value inside A. Otherwise, the program counter will increment by 1. Or if we can look at it from here, if B is equal to 0, go to the value of A, else go to next instruction. Then we have our BZJI instruction. This instruction is the jump instruction. You do not do any checks for B. Instead, what you do is you jump to the value here, which is the value of A plus B. So it is not the value of B, but just B, meaning that if it says B, say G, I, 5, 3, this would mean, well, let's say 5 has 2 in it. So this would mean, look into 5, it is 2, and then we have 3, so PC would be equal to 2 plus 3, which is 5. So now that we have reviewed the instructions, let's look at an example. This code is the code you'll be running in your simulation as well. So let's look at what's happening here. So first up, we have an add instruction, 10, 15. So in 10, we have 0, 15, we have 2. So if we add 2 and 0, we get 2 into 10. Then we have add I, meaning that look it into A, we have 2, and then add 20 to it. So now this is 22. And then we have a BZJ instruction. BZJ 3, 5. So we should look at the value of 5. It is 0. So if it is 0, we have to jump. We have to jump to the value inside 3, meaning that's 7. So from 2 to 7, we're going to jump here. Now we have another BZJ instruction. Here, we're going to check the value inside 10. So the value inside 10 is 22, which is not equal to 0, meaning that we will not jump. So we will continue to the next instruction. And then our final instruction is a BZJI instruction. So what we'll do here is look into the value inside 9, 8, and then add the value here in the B. So we will add 0 to 8, which is 8. So it will jump to 8. This instruction will jump to itself, and we will end our program.